The product property of radicals is one of the most important properties we'll use when we're working to simplify radical expressions. It says that the nth root of an expression multiplied by the nth root of another expression is equal to the nth root of the product of those two expressions. So a simple example would be the square root of 7 multiplied by the square root of 7 is equal to the square root of 7 times 7, or 49. And you know that square root of 49, the principal square root of 49 is in fact 7. So to use the product property, generally we're working with a radical expression that has a radicand that's not a perfect square. Perfect squares are these numbers. We know they're square roots, but 48 is not a perfect square, but I do notice that 16 times 3 gives me 48, so that when I look at the square root of 48, I can say, well, I really see the square root of 16 multiplied by the square root of 3. Now this is helpful because, well, now we know the square root of 16 is 4, and so the square root of 48 can be written as 4 times the square root of 3. Sometimes we'll say 4 root 3. Do the same thing with 5 times the square root of 90. Now I go through my list of perfect squares. I say, well, 4, 9, 16, 25. I can keep going. I want to find the largest perfect square that divides 90. In this case, it looks like number 9 divides 90. And so I can rewrite the original expression using the product property as 5 times the square root of 9 times the square root of 10, because 9 times 10 is 90. So now I go through and simplify each of the square roots if I can. So the square root of 9 is 3, so I can rewrite it as 5 times 3 times the square root of 10, which is the same as saying 15 times the square root of 10. And this expression is in simplest radical form because the 10 does not have any factors that are perfect squares. So this would be my simplified version of 5 times the square root of 90. You can do the same thing if the index, 3 in this case, is not a 2, usually working with square roots, but here we have a 3. And so instead of looking for perfect squares, we're going to look for perfect cubes as factors. And so start with 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125. And I can use these numbers because these are numbers I know the cube root of. So when I consider the cube root of 24, well, I know that it has 8 as a factor. So the product property lets me write it as the cube root of 8 times the cube root of 3. Well, the cube root of 8, let's see, that's 2. And so 2 times the cube root of 3 would be the final answer. Notice the index stays the same throughout. This is still the cube root. I don't know the cube root of 3. It's an irrational number, so I just leave it. And my final simplified answer is 2 times the cube root of 3. One final example involving a variable is the same principle, just a little more abstract. Use the product property to simplify the cube root of 8 times x to the 10th. Well, right away I see the cube root of 8. That'll be easy to work with. And I can rewrite the cube root of x to the 10th as, well, x cubed times x cubed. That gives me 6 x's, but I need 10. So times x cubed times x to the first. So I have 3, 6, 9, 10 x's being multiplied together. I chose x cubed because I know the cube root of x cubed. If you wanted to, you could rewrite it as the cube root of 8 times the cube root of x cubed times the cube root of x cubed times the cube root of x cubed times the cube root of x to the first. So I can go through and say, well, cube root of 8 is 2, cube root of this x cubed is x. The cube root of x cubed is x again. The cube root of x cubed again is x. And I don't know the cube root of x the first, so I'll just leave that as it is, the cube root of x. So my simplified answer would be 2 times x cubed times the cube root of x. So I'm still trying to end with a radicand that has no perfect cubes, in this case because my index is 3.